Okay, so as requested, some of you were hoping for some extra practice on some of these problems that we're doing, whether they are energy types or maybe even like this problem. I still think that we, maybe as a group, some still struggle with these inclined planes. So I'm just going to give you a couple moments to copy these down, and then we'll proceed forward from that. So if I keep looking down at this pack right here, it's just to see if the batteries are still going, because I don't want to continue on if the batteries are dead and there's no sound. So go ahead and take some time to write those problems down. Or I guess another aspect you could do is possibly just hit the pause button, because I really think that if you really want to get a full benefit out of this, I don't think it's going to be much help if we just continually solve and you're just writing down what it is we're doing together as a group. I think it's better, again, if you attempt this by yourself. Then if you get stuck, then go ahead and proceed a little further. So it's at this time, I think it'd be a good idea for you to hit pause so you can copy those problems down. Because we're kind of in a bit of a time constraint here. I'm going to try to keep this short so we don't have to have a lot of time occupied on your part. And with this first problem, okay, we're looking, it's kind of a review because we're looking for a force, a momentum, and the kinetic energy in this scenario. So let's make sure that we can read it. It says, an eagle spots a rabbit while flying at 12.45 meters per second. And in 2.25 seconds, the bird strikes at 15.65 meters per second squared. What is the force? I suppose you could say placed into the rabbit, how much momentum was placed into the rabbit, and then finally the amount of kinetic energy placed into the rabbit or animal. Its mass, that is that of the eagle, is 7.45 kilograms. So again, this is part of your matching portion that you're going to see on Monday. It's important to know what these variables are telling you, because it's not coming outright and saying this is the momentum, this is the mass, this is the velocity. If it is a velocity, what type? Is it an initial or is it a final? What's the acceleration? And other variables that we may be looking for, because we're solving for force. So we know that's going to be measured in newtons. We know it's a momentum, so that is a mass per meter per second. And then finally, the amount of kinetic energy is joules. All right. So I can't stress this enough. The first thing that you should do is hopefully, if you had hit the pause button, you are going through this and writing down the information that you know. So therefore, in this case, we don't even have to write for sure which velocity this is. We know it is because it's measured in meters per second. So I'm just going to put V equals 12.45 meters per second. Okay, and we have 2.25 seconds, so we know that is a time. Okay, and then it strikes with 15.65 meters per second squared. So hopefully, again, by this time, we know that the variable for this is that of an acceleration because it's meters per second squared. So notice we're trying to find a force, a momentum, and the amount of kinetic energy placed into that animal. Oh, there's one more, the mass. Okay, 7.45 kilograms. Now, right off the bat, we can find the force fairly quickly, okay? Because that's just, of course, mass times acceleration, and we've got those two variables right here. So finding the force would be fairly simple. And in that case, let's see here, we've got 7.45 times 15.65. Therefore, that gives us 116.60 newtons. That came from force equals 7.45 times this acceleration, 15.65. So our force had equaled 116.60 60 newtons, rounded to the nearest hundredth. So 116.60 newtons. Okay, so we've got this one taken care of. And that with momentum, okay, we know that that is mass times the final velocity. But one of the things we want you to think about, the terminology in here. Look at what it's saying. It's flying at this speed. Then, in 2.25 seconds, the bird strikes. So in other words, it happened later. So the speed went from 12.45 to all the way up to an acceleration of 15.65. So something there had changed, and it's the velocity. So if that is the case, that makes this an initial or final. I want you to think about that for just a moment. And again, the terminology hopefully helps you in that problem. If it says 2.25 seconds later, or I should say in 2.25 seconds it strikes. So it happened after it was moving this speed. So if you wrote down this as the initial velocity, that would be correct. So we don't have the final velocity. So we can't solve for that momentum because we have to have that final velocity first. So what I want you to do is look at this information and think, okay, can we find that final velocity? And of course the answer to that then would be yes, from this formula, because we know that the acceleration equals Vf minus Vi divided by t. And more often than not, well, I shouldn't say more often than not, but the amount of the final velocity is much easier to find than the initial. So acceleration 15.65 equals velocity final minus whatever our initial velocity was, which is 12.45. And of course, that's all over 2.25. Now, we've done this step multiple times. Okay? I want you to think about what is it that you would do next to help solve that final velocity. And again, maybe hit pause or see once what it is that we would actually do. Because I see we're running up to almost 8 minutes. And again, we've done this since the first or second week. We can always put that number over 1. We have not changed anything. So now we cross multiply. So 1 times Vf gives us Vf. Okay? Then 1 times a negative 12.45 gives us negative 12.45. We cross multiply here, so we'll cross multiply those two. And with that, it looks like we're going to get somewhere into the mid-30s, perhaps. 15.65 times 2.25. That gives us 35.21. That was just a lucky guess. I can't calculate things that fast. Okay, so we had 35.21. Again, we haven't solved for anything yet because we just have this equation. Okay, so we need to get that Vf by itself. And notice that we're subtracting here. So to undo subtraction, what do you think we're going to do? If you said we're going to add 12.45 to each side, that would be correct. Okay? So we're going to add 12.45. So we're going to add 12.45. They're gone, so the final velocity now equals, okay, 35.21 minus, excuse me, not minus, plus. I was just seeing if anybody's paying attention, and perhaps you were, unless you're doing this at midnight on a Saturday night. I sure hope not. We got better things to do on a Saturday night, I think. like maybe watching something on Freeform or a Christmas movie to entertain yourself, because hopefully we can see the benefit in this, that we've all worked hard to get to this point. So 47.66. And again, that's meters per second. I got 2 decimal places there. So I'm going to take this one out. So now that we got our final velocity of 47.66, I guess I can erase all of this material here because we don't need it, because we have everything wrote down in our setup that we need. The last thing we're going to do is solve for that kinetic energy, okay? Because I'll leave it up to you to solve for that momentum, and I'll just say what the answer is, and hopefully you can figure out what it is from that point in time. And is 355.06 kilograms per meter per second. So the momentum, or the product, equals 355.06 kilograms dash meter over second. And in short, what you're doing is you're taking the mass times the final velocity to get that momentum. That's where that comes from. Okay, the last thing we need to do is find that kinetic energy, okay? And in this case, that initial velocity would not have helped because it has not struck the animal yet. So if we have a mass, okay, and we've got a final velocity, and human error can lead to this too, and I'll show you what that means, what I'm getting at. We know that kinetic energy, doing what the formula tells you to do. Okay, I'll let you maybe catch up for just a moment to see what it is that we would do. Okay, so KE equals, okay, I'm more so of a person, I like the mass times the velocity squared on top. So we've got 7.45, there's the mass. We found the final velocity here at 47.66. And again, that's all over 2. That's human error. You may forget to square that, okay? Or if we were given the kinetic energy in this case, maybe we would get it down to whatever that is squared. You got to take the square root of that. We did that today in class. Okay. So what we're going to do is take 7.45 times 47.66 times 47.66. It's going to give us a really big number, about pretty close to 17,000. Then we got to divide that by 2 yet. Divide by 2. That gives us 8461. There's a decimal place that goes along with that, but kinetic energy equals 8461. Point, I think it said 24, and again, that's in joules. Okay, and that's how we would solve for the kinetic energy in this problem. Okay, I'm running, we're up to 14 minutes, so now I just want to keep on going with this inclined plane. And one of the things we said in class, don't feel bad if you're drawing a diagram from that. Some people may be more so of a visual learner from that. Okay, so what we see happening, this really has nothing to do with the problem. It's just telling you how big that winch is that's pulling that equipment up this ramp. Okay? So, if this helps, by all means, do that. Okay? All right. So it says we've got this dozer going up the ramp. Its mass is 8,900 kilograms. Okay, so that's being pulled down, of course, by gravity. We have to account for that. Okay, and this was 8,900, is that right? Yes. A 40 horsepower winch is pulling a dozer up a ramp that is 26 meters long. The height is 2.45 meters. The mass of the dozer is 8,900 kilograms. The winch is pulling with 8,800 newtons. So what that means is as that is pulling up that ramp, is that a resistance force or an effort force if it's saying that it's pulling with 8,800 newtons? And of course, it's at that point in time you'd say, yes, it's being exerted on that, so it's being moved in this direction as an effort force of 8,800 newtons. We know it's a force because it's labeled in newtons. All right? So for how long is that 8,800 newtons, or how long is that winch pulling up that dozer? Well, it would be the length of the ramp. And according to that, it's 26 meters long. And then the height that gravity is having an effect on, or the resistance from that gravity, is 2.45 meters. Okay, I guess you could say kilograms here. So now, the next thing we want you to do is we know, I guess it's not saying, we're looking for the efficiency. I guess that's one of the things I should have said. What is the EFF? Yeah, I think this could be fun. Not only is it the EFF, maybe this is your BFF. Ha, 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 ha. We told a funny. Okay, I'll wait till you stop laughing so you can get back to work with this. BFF. All right. So anyway, with that, we're looking for this. Okay, in that formula, we need a resistance force, we need an effort force, we need a resistance distance, and we need an effort distance. So now that we got this diagram, we know that that winch is putting an effort of 8,800 newtons pulling up on that ramp. So 8,800. Okay, so the resistance from gravity pulling down on that 8,800, this doesn't give us a force, but of course we learned from the prior example that the mass times acceleration would give us this force. So 8,900 times 9.8, that gives us the resistance force. So for how long is that winch pulling? Well, the length of the ramp, and that length is 26 meters. The effort distance is 26. And then from gravity pulling down, the height of the ramp is the resistance distance. So that is 2.45 meters. Okay. Now, if we would see all these variables and not asking for the efficiency, that would be one where we gave an example of maybe a farmer swinging an axe, or we're pulling a nail, how much effort must go into it, how far is the nail moving. But if it is saying anything with efficiency, we're using that formula where it's FR times DR over FE times DE. We've got everything set up. So now what we need to do is do what the formula tells us to do. And that is the efficiency equals the resistance force, which we haven't calculated yet. We can do that right quick by taking 8,900 times 9.8. That gives us 87,220. 87,220. Okay, and it's also times the resistance distance, which we had said is 2.45. Okay, and then that's all over FE times DE, so 26 times 8,800. Okay, so now 87,220 times 2.45 That gives us 213. 689. Isn't that funny joke why 6 was afraid of 7? Because 6, 8, or 7, oh, 7, 8, 9, that's what it is. Yeah. So, yeah, maybe that's why it's gone. Because the 7, 8, the 9. Okay. So therefore, these two times each other. 8,800 times 26, 228, 800. Okay, we haven't quite solved for it yet, so 213, 689 divided by 228, 800 gives us about 94%. So efficiency, it's actually 0.93339. We're going to round that up to 94% efficient. That's what we're looking for, according to that ramp. All right. So hopefully you can find that gives you a little bit of comfort if you've done well with this and we understand these concepts. If this had made sense, that top one was probably one of the more difficult ones where you had to find the kinetic energy from that. So again, if you have any problems, please get in and talk to myself and we'll move forward from there. All right, it's Friday afternoon, so have a great weekend, people. Catch up to you next time.